Hi, my name is Alex and I'm a Senior Staff Cloud Engineer at Ocado Technology. Today I'd like to share with you our journey over the last decade in building an internal developer platform that allows our developers to increase their autonomy and innovate at scale. I want to show you what we've tried that has worked and what hasn't, and also some of the general lessons and patterns that could be repeated from our product today. But before that, I want to take a minute to introduce to you who Ocado is and our journey to give some better context to the platform we've built. Ocado started as a pioneer in the online grocery delivery industry in the UK back in the early 2000s. Our first generation warehouses relied on a system of kilometers of conveyors, moving thousands of containers of groceries. We've completely redesigned that model, and today our automated grocery fulfillment warehouses use thousands of bots running on top of a three-dimensional grid of products. As we follow this journey of innovation, we've continued to evolve into a global technology company, and we now provide an end-to-end platform for online grocery to some of the world's largest grocery retailers. To illustrate the scale of our growth, we've deployed 19 of these automated warehouses, or fulfillment centers to date. In 2023, we'll be launching another 5, with more than 50 planned globally in the next few years. Since we provide our retail partners with a fully end-to-end solution, from e-commerce to fulfillment, logistics, and supply chain, we have a broad range of applications that will run on our platform. We have customer-facing, front-end web applications that are image and static content heavy, with cyclical request loads that follow daily and weekly customer shopping habits. And we have compute-heavy, RAM-intensive applications that optimize our delivery van routes. And we have real-time, low-latency wireless robotics control applications. And all this needs to scale during peak online shopping events, such as we saw during the global pandemic. We also have developers spread across the globe. We need to ensure they all have equal access to our platform and tooling. We want to avoid a situation where you know someone in ops and you draw some chocolates at their desk to make sure your tickets get to the front of the queue. Although we started from a single development center in the UK, the ratio of engineers working on our platform to the rest of the product engineers across the globe has always been in the low single digits, and we need a solution that will scale with the number of users we have. Even though we have that large diversity of application types, we want to try and simplify our tech stack by having some best practices and golden paths to follow. This makes it easier for new starters to learn, and easier for engineers to collaborate or to swap between teams. We can also make the platform more developer-friendly by releasing language libraries that make best practices repeatable. For example, we have a Java library that allows a developer to get a Java application with OAuth 2-based authentication deployed in minutes, with loads of features like health checks, logging, and monitoring working out of the box. If you'd like to learn more about our best practices for software development, we publish our developer handbook at the above URL. Although this talk focuses on the platform journey, it's a great resource for developers. So, around 9 years ago, we had this opportunity to redefine our platform when we started our migration to the cloud. Platform engineering wasn't a term at the time, but we started with a desire to achieve a few things. We wanted to be cloud native. We started just building a platform for those applications outside of our fulfillment warehouses, such as e-commerce apps, which were a great fit for the cloud at the time, as it was still a new technology to us. We wanted to embrace a DevOps culture and then the separation of developers from the practice of operations. And we wanted to build developer self-service at the center of our products. To enable this, infrastructure teams would act as software development teams, with product managers, agile methodologies, and prioritizing automation, APIs, web apps, and infrastructure as code over manual toil, ticket, and operational scripts. We wanted to use native cloud managed services over self-managed services, and all data and functionality should be exposed through service interfaces. Those familiar with the history of Amazon will see this as a bit familiar to Jeff Bezos' mandate back in 2002. By 2012, this had evolved into a core part of the microservices philosophy. With that in mind, one of the first products that became a core part of the platform was an application registry. In order to offer services to developers, we need to know exactly what applications exist, who owns them, and where they're deployed. We can also offer useful features like links to documentation and source code, dashboard, contact information, etc. Above you can see a screenshot of the UI, but everything is also always available over a RESTful API as well to support automation and integration. So, one of the big decisions and debates in building the platform early on was whether the underlying runtime of the platform should be exposed to or abstracted away from developers. At one point, we had a Kubernetes platform running on premises that developers authored and deployed Kubernetes manifests to for every type of resource they needed. And we had an AWS-based platform that abstracted away details of the Elastic Container Service and the Relational Database Service to offer developers a minimal and simplified interface. This debate balances the autonomy of the user and the mental load placed upon them. Now, in my experience, developers do not want to have to learn more than they need to complete their daily tasks, like deploying an application or resizing resources like database. And in the end, we went with this abstraction model, meaning that we can precisely offer exactly the platform we want to our users and design its API around their needs. So having said that, one of the actions we've abstracted is deployment. So what does our deployment service look like based on our philosophy of self-service and abstraction? So we built a RESTful API and embedded it into our registry that would deploy an application for a user or a team. This becomes a huge benefit also if you do any audit or compliance activities, because you now have a central log of all production changes to, for example, check against your change management process. So to start a deployment, a user just needs to make a post HTTP request to a URL that looks like this. And this includes what type of environment, such as development, test, or production environment, what business it's for, and what application ID it is. Included alongside that post request would be a payload. So this is the absolute minimum a developer needs to provide, which is just some JSON that says, here's my code. It's a Java application with this Java version, and we use default values for everything else. So they'll get a default value for things like CPU and memory requirements. And as a user becomes more familiar with the deployment tool, they can return to this simple deployment and add additional parameters to customize it to their needs. Now, behind the scenes, we're doing a lot on behalf of the developer. We're creating DNS records, load balancers, security groups. We're building and publishing a Docker image and creating an ECS task and service with auto-scaling. And when the application has been successfully deployed, the user will have a URL, which also has a corporate single sign-on in front of it. So here we can see a dashboard for my previous application of all the environments or applications it's been deployed to. So we can see things like the current health status. We can find out the URL. We can see what runtime it's running on and things like that. So alongside the idea of abstraction, we also had debates over how much access a developer should have to production environments. Now, on one hand, developers need to be able to support their applications during an incident. Some users were very used to having permanent SSH access to their production VM, for example. However, we found when we removed SSH access for security reasons, users did not complain and developed new workflows and ways to achieve their needs. As before, the solution is going to depend on your organization, but making restricted and temporary access part of the platform is something I would highly recommend. And in fact, we could use our product development discipline to find out what users actually needed beyond SSH when they were supporting a production incident. So another feature that we built into our platform to support this is the concept of approvals. So certain application changes might require an approval from an owner or a stakeholder. And a developer might need to request temporary access to a production database, for example, to support an application. Here, such requests can be made, audited, and access could be granted on the basis of an approval. It's very important for us also to be able to measure the metrics for our platform. And you can use these to drive our product development in addition to user feedback or feature requests. So we have some key performance indicators or KPIs. So firstly, the number of weekly code deployments we have, the average duration of a deployment, and the number of applications on our platform. And since there are many teams that maybe started off on a different solution internally and migrated to ours, we kind of want to check that these KPIs are trending in a positive direction, as one of the key benefits of building a service between your users and the underlying cloud infrastructure is that you can measure anything and everything. And many application teams are big users of observability tooling to better understand and monitor their business applications. We try to be the same with our platform. Often, a problem you might find with internal developer platforms is users are sort of obligated to use it. They have no choice. So it's really important to try and get feedback when you can, work out if people actually enjoy using your tools and if they would choose them over something else. Another key benefit of our abstracted platform is that we do have some ability to make cost savings without needing to have developers change their ways of working. Here we have an example of how we managed the underlying compute resources for our runtime. So Spiky peak usage is fulfilled with a mixture of cheap spot market instances and more expensive on-demand instances. But the bulk of our stable committed usage is covered by a committed spend savings plan that most cloud providers will offer in one way or another. So, we'd initially built a platform suitable for purely digital applications in the cloud, but what about the applications I mentioned in our physical fulfillment centers? So this is a more challenging case and an example of a potential platform customer that an out-of-the-box solution might not have been able to cater to. So a little bit about how our bots work. The bots are orchestrated by our proprietary AI air traffic control system to collaborate to pick customer orders. The bots themselves are not autonomous and do not make their own decisions. They're traveling at speeds of 4 meters per second with just millimeters of clearance between them. And this 3D grid is the world's densest automated storage system that we know of. Now, that wireless technology is communicating with each bot 10 times a second. Bots are also uploading their data to the cloud where it's analyzed by smart machine learning for preventative maintenance. So our air traffic control communicates orders to the bots over our own communications network. And any bot requiring preventative maintenance can be instantly replaced, no loss of throughput. To give an idea of the size of data we're talking about, each bot records about a gigabyte of data a day, so this could be 4 terabytes of data for an entire swarm. So, historically, we've deployed our bot orchestration system on premises, running on local compute in server rooms in immediate proximity to our bot fleet, with a high-speed network to ensure the predictability and messaging delay required to achieve the optimal throughput. This is essentially a full private cloud with all the overhead that this comes with. However, given the success of our cloud platform, we wanted to see if we could run our bot orchestration system in the cloud. Pictured here is the architecture we designed. So using a site-to-site VPN between AWS and our warehouses and a network load balancer allows us to deliver the consistent latency requirements for this workload. And provided our fulfillment center is physically close enough to a cloud data center or a region. Although some parts of this architecture might seem like they're bespoke to this one application, because of our abstraction philosophy in designing the platform, we were able to just add these configuration options to our APIs so they could be just used by the teams that need them. And other applications or teams were unaffected and did not need to be aware of this migration. So that's been a little bit about our journey. And what I've shown you today is based on the products we've built ourselves internally over the years. But if you were to try and replicate these today, rather than building them from scratch, there are some available managed services that you could use instead that I want to recommend. So in order to have an application registry like ours, I would recommend looking into something called Backstage. This was created by Spotify. Backstage is an open source software catalog and a highly pluginable developer portal that would allow you to build an UI for managing and discovering all the applications in your organization. Now, although it's attempting to be the worst named AWS service, Systems Manager Change Manager provides a service similar to our approvals product as well. And then if you are doing a big migration of a large Java or .NET workload into the cloud or into a containerized runtime environment, such as Kubernetes for the first time, coming from legacy VMs or from EC2 instances, then apt2container is a free command line tool that may help you with your initial containerization and CI/CD migration. Alternatively, build packs was something first conceived by Heroku back in 2011 as a way to transform your source code into a containerized runtime. And since then, they've actually been adopted by Cloud Foundry and other platforms as a service and joined the Cloud Native Computing Foundation in October 2018. There's a lot more that I would love to tell you about the last 10 years. It's been really exciting watching the growth in understanding of the platform engineering craft. We're excited to see where the next 10 years takes us. We're also hiring, so if what I've talked about today interests you, then search for Ocado Technology Careers online to find out more. And that brings us to the end. Thank you very much for your time today, and I hope you've enjoyed our story of our journey into platform engineering.